Alright, what's up everybody? We got a special iteration of the pantry stream for you today. So as you can see right in front of you, we're analyzing some Smash Brothers. Boy do I love that. So we got Luigi. I'm not sure if you know this, but Luigi in Melee, he is a slippery boy. And we will see by these calculations. So what you're seeing in front of you is basically, I can also show you this, but basically I took this video, shoutouts to Jacob Stair by the way, and yeah, I just took basic video of wave dashing because I do not own Melee right now, unfortunately, so I just took that for this segment, and yeah, we're gonna see what that's like from, you know, kinetics to whatever we want. So let's get into it. Alright, so first off, we gotta settle down a few things. So Luigi is 90.7 kilograms. That's his weight, and he is 155 centimeters tall. So now that we've got that out of the way, that's just the common consensus. Not sure if that's lore or not, but anyway, here we go. So I measured, so this first on the left here you're seeing is the start of his wave dash. At the end there is the end of his wave dash. So we got T equals 14 divided by 30 FPS video here. Probably could have got a 60 FPS one now that I look back at it, but does not matter really. It would be very close to the same. And then we have because it would be very close to the same. And then we got the distance carried over from 155 centimeters. So, oh man, I forgot to start the timer. I just realized. Let's not get sidetracked. This is a speed run by the things you see at the bottom there, but I'll retime it in the VOD. We're good. I'll put the timer on. Anyway, so let's keep going. So I measured the velocity with that equation there to be 6.64 meters a second, and in this, I'm pretty sure you can see my mouse. I got the Luigi. That's how I measured it, just like, you know, using him as a basis. His melee height's kind of weird, I feel like, but I mean, that's just what we're going off of. So now we can go to the next part here, which is its acceleration. So using the kinetics 2D formula, vector formulas, I got it to be 7.11 meters a second squared. Sounds about right. Sounds about right. So with that, oh, there's a lot there. Also, that I forgot to mention, the 6.64, if you were curious, is 23.9 kilometers an hour. Excuse me, and that means he is not Usain, but it's pretty good speed for barely moving. As you can see from that video, he just slides around and he barely moves his legs. So yeah, we're gonna find, so my goal here, we want to find the force of friction mainly. That was my main goal. Like, what's the force of friction based off Luigi in this sense? Because obviously the physics of each character is different, but I mean, just for Luigi, this would be pretty interesting. So we rewrite the equation, cancel out the masses, we get 0.72, pretty low, which sounds about right to me. Yeah, so we're gonna move on with that. I mean, it's not too low, right? It's about average actually, but yeah, I mean, I guess that's expected. With the infinite mod, I was actually originally going to use the infinite wave dash mod for this, because that's hilarious. That's hilarious. It's just like pretty much he never stops sliding, but obviously his friction would be like as close to 0 as you can get, or just straight up 0. So moving along, we found that the force friction is actually 640 newtons. So that means, I mean, that's pretty cool, I guess. So we can, just for fun, we could get the momentum, 602 kilogram meters a second. Not too bad. Not Usain, once again. Gotta repeat that fact. And then look at that. we got the F net. So I think I did this right. So force of friction would obviously subtract. So that makes the mass times acceleration 645 newtons. Got the applied to be 1285. So I guess the wind is applying that, because he straight up barely moves his legs, as you saw. So I guess we're gonna call it wind. That's what most people call it, like there's a wind cloud behind him. So it kind of makes sense. But you know, wave dashing IRL got some problems to it. So here's another image over top of that. And that's just the jump that you sometimes need to start for the first one, so I just decided to, that's how I got the work of this to initiate it. Technically it takes that many joules, but not really, because once you get going, like the one I based this off of didn't take any technically, because you don't really have to jump. You don't jump at all, you just slide. But if you did jump for some reason, there you go, that would be the joules. Alright, so let's move on to the next part here. So I guess basically we can summarize this to take it to the real world. It's like, it's basically impossible unless you have constant, like, I don't know, super high powered invisible fans around you, because that's kind of how this works, is how we could apply it. But yeah, that's Luigi's the friction from Luigi and all that, and all the calculations to go along. Beautiful paint document. Alrighty, so I got a treat for you. So what you have in front of you is my almost let's see here, it's like 8K, over 8K image. Pretty big image, almost 10K actually. So let's zoom in. Why don't we? Because I made it that big. Flexibility. Now looking back, I could have just cut out the out of bounds, but yeah, so based off just a simple screenshot like this, I decided to, you know what, let's get as much info as we can on the planet. So I'll just show you the visuals for that, and we can do a little bit of math after. So, you know, there's, you know, this is where the action happens, at the top where the trees are and such. So actually when you zoom out, like in this blurry image in the back, you can kind of see that it shows a little bit more than the map, because I got a zoomed out version. You know, those out of bounds videos, shout outs to Boundary Break. But basically, I, you know, formed a circle the best I could using, you know, a circle. And I filled it in just to make it not look disgusting, and still kind of does, but anyway. We use Mario, which I just put in there because I used a different model. I didn't use that, which I almost used this one. That's besides the point though. So rotated him a little, went in, put him over here, counted them a bit, and there we go. 21.5 Mario. So Mario's a bit shorter than Luigi. What was it? All I know is he's 4'9", I'm pretty sure, or 5 flat. One of those. I'll go get my info for that. Be right back. What did I say Luigi was then? I'm curious. So Mario's height is actually 155 centimeters as well, because turns out I accidentally used the old official Luigi head apparently, because apparently there was an old one when they used to be the same size. So, but good thing in Melee that they're basically the same size. He's a bit taller. But, yeah. It's a give or take scenario. Anyway, just thought I'd point that out, be honest. Also, we gotta shoot for that world record pace. So, we gotta keep going here. I'm losing to my false PB. But anyway, so Mario is 155 centimeters. We times that by 21.5 into the core of the planet. Get that juicy radius. This, oh yeah, I thought it was lagging because this is very large, but we're okay. And yeah, so from there, and I forgot to mention, we should probably assume that this is 9.8 gravity, just because it's that's the consistent gravity in Smash, and it's pretty hard to get anywhere else. So we're just gonna say, in this asterisk case, if there's Earth's gravity, then sure. So yeah, this stage is circular. The characters go around, and it has the same gravity as every other stage. So that's what makes it interesting. So, other than like obviously the pull is gonna make them go like around. So obviously, what we're gonna do. Well, actually, my hypothesis was that what they could do is, I'll just read this. So we'll assume that Earth as every stage in this game seems to be consistent in the platforms. Okay, I was saying the platforms likely have some kind of magnetic or gravity canceling float to them, so you know, maybe there's some kind of charge or some kind of consistent floating upward. So there's many ways you can do that, but that was worth mentioning. So we can conclude that this planet is in some sort of Lagrange point, possibly, or that it's rotating very fast. But then I realized that only works with space stations when they're like inward facing. So scratch that off. Or there are energy-hungry magnets or forever accelerating vehicle involved here. Does not look like it. I mean, maybe the vehicle in the background there. But we're not talking about that. Or exotic high-density matter. So, I mean, obviously, I don't think we're going to go with those cases. There's also the possibility they're wearing gravity-defying suits. Which, I don't think it would... It's safe to say they're not. I mean, maybe Mario. But anyway. Yeah, Bowser ain't. So, this is one of two stages that are curved in the Smash Bros. Stages that you can choose from. And, yeah, we could conclude that it's rotating very fast, but that technically wouldn't be our solution. But it is rotating. If you go on the stage, it is rotating. So anyway, let's do the calculations here. So, if it was a space station, I did the calculations anyway because this was my process, so it's worth mentioning. So, just zoom out here for a sec, get it nice and pretty. So, we at Gingermail Labs found that the radius was 33.31 meters. So, yeah, it's just a little tiny planet. So that means that the speed would have to be, I'll just show this on screen afterward, speed would have to be 9.8 meters a second squared, and well, that wouldn't be the speed. Excuse me. The speed would be 18 by the formula G equals big G at big M over R squared. But yeah. Wait, I'm stupid. I'm not using that formula. No, this is using the formula V squared over R. So, using V squared over R, centripetal force, it's V squared over R, not centrifugal, right? We're not using that. So anyway, which should be the case. So anyway, this only works for space stations, so we moved on to an actual formula. G equals big M over R squared. So we put this together, the constant of big G, Kepler's constant, right? And then we ended up getting squaring the 33.3, and then we got that the mass of it was 1.63 times 10 to the power 14 kilograms. So that's what we found the mass to be, going off of it being Earth's gravity. So compare that to the Earth's weight, and it is, or mass, and it is a lot heavier, obviously, as should be. Yeah, that's the mass. So anyway, for an experiment, because I couldn't think of much else to do with this, because we can't exactly say this is in our solar system or anything, but we're just gonna say it is, just for an example. and let's say it's like this planet in the background, or I don't know. We'll go with this, like the moon. We'll compare it with the moon's mass, and we'll calculate an estimated distance here, because obviously there's a third dimension involved, and yeah, we're gonna figure that out shortly. Alright, so as you can see here, I put a little bit of depth onto our Marios, and yeah, we just, you know, because that's obviously in the background, so I tried to bend it quite a bit, just obviously because this is an estimation. So we're gonna pretend that moon has the same mass as the moon, which is a broad assumption to make considering how tiny that looks. But anyway, we're pretending it's in our solar system and this is Earth, because it has the same gravity as Earth technically. So with that logic, we can now say that the force of gravity is not pretty. So doing this equation, which I said this was roughly 35 Marios, counting it out, and which is 1.55 meters times 35, and then we got, for the force of gravity, this is not pretty, 2.7 times 10 to the power of 23 meters second squared. So let's just say it is not happy. No one's happy being there. If this was in our solar system and that's Earth and that's the moon, let's just say that. So yeah, that's actually neat. I'm glad I did that. So anyway, let's get this PB, baby. Let's move on. Next one, NES related question, I think. Alright, so I'm back real quick in post kind of thing, aka about to finish. Yeah, I'm just gonna show on screen the calculations I did. I found the period by doing, you know, 4 pi squared times 33.3, the radius, divided by t squared, and I found t, and I put the gravity as Earth, as we discussed. And if we wanted to pretend that I didn't mix up centripetal and feudal force, yeah, I'll put that up there. It was 106. It's irrelevant. Alright, moving on. Alright, so now we're talking about magnets. So, as you can see with this little clip I made, the magnet draws Mario in, except I missed the first time, and... okay, there we go. Why is it so sped up, what? But anyway, you get the gist. He moves in a bit. I have a better clip here of that. Does not really matter, though. Alright, here's NES's, so we're gonna compare the two. Alright, since this is a speed run, I ain't re-recording more stuff because apparently I messed that up, but you can see here that, see that clear pull on that. Clear pull. And there's a clear pull on the NES one as well, which I'll show again quickly. Is right here. Alright, so I changed my mind. I decided to find out a few things real quick. So, as you can see here, obviously he blows stuff away. Well, not just from the hitbox, the win box. See that? Okay. On a, specifically on a NES, I feel like it's very hard, but on a tall character, it's really easy to blow them away. Anyway, like you can blow them pretty far. That's good enough. So, what I wanted to find out is, let's control player 2. 2 controllers here. How much does PK Thunder, which has up to 1 billion volts apparently, so we're just gonna go on the high end for this for fun. Does 13.2 damage, specifically in training mode. So, and how much does he heal back? So let's hold down B on this controller and go with my other hand here. Oh, heals all of it. So let's put on a little bit more damage. That's actually pretty good. So we give him 18 plus the 13.2 and let him heal up. Give him his breakfast. Alright. Jeez. How much did that heal? That heals a ton. That heals around 18? Yeah, just about 18. Not bad at all. So, ooh, this is gonna be interesting then. Okay. So what we're gonna find out first with the magnet. We'll get into the pulling and all that in a second. But this is my... Yeah, we're doing 2 with Ness here. Technically like 3, but anyway. If he heals, so... If he heals... Okay, so we're gonna do the math. So he does 1 billion joules, we'll say, which it should not do that little damage, let's say that much. And... Okay. So let's calculate this. Okay, so basically on the high end, because obviously this wouldn't be on the high end because this lightning is definitely not from however many feet in the air. But from that, we can determine that Ness heals back around 1.3 times the amount that it does, which means he absorbs 1.3 billion jolts, and basically, or 1.3 times 10 to the 9 jolts, and basically he would either die on the spot carrying that much, or he would, if clearly he can resist this stuff, like, yeah, he would be able to power, how many houses is that? I think it'll show on screen. I think it was 59 to, it was a 59 town, or 59 house town for a day, which, that was just 1 billion, so he can do 1.3 times that. I'll put the math on screen. Pretty sick. Alright, I'm back after some technical difficulties and having to redo a few things, but it doesn't matter, we kept the timer running. So yeah, I did something crazy, and I used this video to capture that with that crisp noise to get to here. So we're using this Ness ruler here, as you can see, and I ended up determining that that distance is 11.5 inches. He knocks them away after magneting, which is roughly a foot, so 3.5 meters was my calculation of that. So we got the time, 6 frames, and then that was our velocity from that. So a human can hold 3,000 volts. So this is where it gets a bit complicated, because we only usually do charge equations with like electrons and stuff of the sort. So this is where it gets a bit interesting. So, which this could very well be wrong, obviously, but it was worth a shot, a bold move on my end. So, so you call 3,000 volts. So we're gonna be using the equation, voltage equals work over charge. So we decided to use kinetic energy, which is half times mass times velocity squared. So we used the estimated weight of 59, or mass, sorry, but everyone calls it weight online. 59, well, at least when looking this stuff up, 59, and that was a combination of his cannon weight and mixing with some smash. It's his cannon weight, but we mixed it with some smash lore kind of thing, because he is heavier than Mario in this game. Just does not make much sense if you compare his weights, unless this is you know, time skip Ness or something, which wouldn't make much sense either. But anyway, so as we, or I don't know, maybe we can have some crazy theory where he's from, you know, his planet has different gravity and he's adjusted to that, his matter's different, I don't know. But anyway, let's continue. So that, I mean, which kind of would make sense because of all the energy he holds, but anyway, that's a different story. So we get into this we got his weight and his velocity as before. So we get 9,300, alright, 9,034 joules roughly. So we can do the equation. We get charge of 3, because we use 3,000, we're just going on the high end of voltage. So the electric force here we're gonna get out of this number is going to be, which we're gonna use 3 on each, and I guess it makes sense in this scenario. So we put the equation in there with the 3.5 and the constant. We get 6.6 times 10 to the power of 9 newtons. So from there, so now we can, I guess, get the electric field. So from the electric field strength, I guess the magnet in this case, which we can say is an electric field, we get 2.2 times 10 to the power of 9 newtons per coulomb. So it's pretty neat. Pretty neat stuff. I did not expect to get something like that. But then again, this is normally done on electrons, so this is all theoretical. Maybe if they're electrons and they can hold electricity and do literally everything, you know. It's hard to explain, but yes. And it's worth noting, if you wanted to pull in, probably just change one of the charges, which would make this negative if it was Lucas, because it roughly pulls in around the same, but it's a lot easier to pull in from actually no, that wouldn't be right, but you get the idea. If Ness was like Lucas, we could just do that. So yeah, it's pretty cool. Alrighty, so I guess we can hit time on this as soon as we see. What was the rule for this category again? I think I'm just typing done. Okay, oh. Alright, I'm gonna have to retime this hard. Come on. The heck, my timer, it won't stop. It's broken. Alright, there we go. 1:53, sub 2 hours, not too bad. I mean, considering I had to redo some of the segment, but it's okay. Not quite my PB, but I'll take it. So yeah, I hope you learned something today. It was pretty groovy, pretty fun. I actually had 2 more that I just scrapped it because I don't have time. Also, that's technically 4. Maybe I'll quickly. Alright, so yeah, we just did a quick bonus option of what rocketing does. You know, we measured it out. I mean, I have it all here. I'll just show it here so I don't have to do it in posts. 59 kg. So we got his time it takes for a rocket to happen, 17 divided by 30. Then we got distance using our Ness ruler, 6.63 meters. So we got that velocity, this is how many kilogram meters a second. And with this, we can do pretty much those momentum 1 equals momentum 2 equations, which I would have done, but I am low on time. But it's very neat. And yeah, you could do that with pretty much any character, and it would probably work. We just need to get the mass and velocity of our user. So if we're doing Mario, we just gotta get his velocity, and yeah, afterward, and the transfer of momentums, yeah, because transfer momentum is actually kind of accurate in this game, because if you can see, it actually, you know, he actually goes less far. Like, he actually stops a lot faster. So yeah, it's pretty neat. Anyway, I just wanted to mention that because I have no time. Alright. Alright, thank you, Pantry Crew, for watching once again. As always, go eat some bees. Alright, I'm out. Cyber salute to you. And be sure to leave your times down below because, I mean, we gotta push the meta for this category. Anyway, Godspeed.